In this video, we solve problem 7.1.022 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following functions. F of x equals the cube root of x minus 7, and g of x equals x minus 7. We're asked to sketch the region bounded by the graphs of the functions and then find the area of the region. Now, one thing that I don't like about this problem statement is that it labels one of the functions f of x and one of the functions g of x. And we have that formula for the area between two curves that features an f of x minus a g of x. I don't want you to get distracted by these labels at all. I want you to think of this as one function and this is a second function. This is not necessarily the top function where this is the bottom function. We actually have to graph them first and then decide which one is the top function and which one is the bottom function based on our picture. So first we'll start with our sketch. G of x equals x minus 7. That's the same as something like y equals x minus 7, where y is equal to g of x. This shows us that when x is equal to 0, y is negative 7. And when x is equal to 7, y will be equal to 0. So g of x, that's our bottom curve, it's just a line, and it looks like that. Or I'd say our bottom curve. It's our second function, and it looks like that. Now for our other function, we have this f of x. F is the cube root of x minus 7. So when x equals 7, f of x is equal to 0. You can also think of this as y equals the cube root of x minus 7. And when x equals 8, y is the cube root of 8 minus 7. The cube root of 1 is 1. And when x is equal to 6, we have 6 minus 7. 6 minus 7 is negative 1. The cube root of negative 1 is negative 1. And the cube root function looks like this. So our region is actually this very tiny region right here. And so I'm looking for a graph that looks like this in WebAssign. Okay. Now, if you're not sure, if you're not 100% sure that that's the shape, you know it went through those 3 points, but you weren't sure that it looks like that. Hopefully you can remember from pre-calculus that a cube root function tends to have this shape. You could also plot some additional points. Like you might try x equals, well, I guess 15 here would work, so that we have 15 minus 7, and that would give us an 8, and the cube root of 8 would be 2. So you would know that when you plug in 15 here, the y value would equal 2. So you could plug in a couple more points, and then hopefully that would help you remember that the shape of the cube root graph looks like that. Okay, so now we want to find the area of the region. And this is where you want to ignore these labels f and g, and you just want to look for the top function and the bottom function. Now I want you to notice that on the interval from 6 to 7, the line is the top function. That the line is above, the y values are higher on the line than they are on that cube root graph. So when I find the area, I'm going to have to split this into 2 pieces. On the piece, on the region where x is between 6 and 7, the top function is the line, which is given by x minus 7, and the bottom function is the cube root function, which I'll write as a 1/3 power, because we know that a cube root is the same as this x minus 7 to the 1/3 power. That's just applying this fact from pre-calculus, that if you have the cube root or the nth root of x to the m, that's x to the m over n. This goes in the denominator, m goes in the numerator. Oops, it's a 7, not a 3, sorry. Got caught up in the 3 from the cube root. So this is the top function minus the bottom function on that interval from 6 to 7. But on the interval from 7 to 8, the cube root function is on top. It has the higher y values, and the lower y values are on the line. So we'd have to add the integral from 7 to 8 of the top function minus the bottom function here, but they switch. The top function this time is that x minus 7 to the 1/3 power, or the cube root of x minus 7. And the bottom function is given by the line. Don't forget your parentheses, because that line has 2 terms. We're subtracting both of those here. So our area is given by this. We'll just evaluate each one of those separately. I'm just going to use A for area. In each case, we will apply the fundamental theorem of calculus. So we'll compute an antiderivative, then we'll substitute in the bounds, and then subtract. So when we're just subtracting this binomial, we can distribute that -1 to each term. That'll give us a negative x, and a -1 times -7 is a positive 7 there. Okay, so now we just need to evaluate this and this. Well, to evaluate this piece, you just use the power rule when you're taking the antiderivative. So you add 1 to the exponent and divide by the new exponent. The antiderivative of a constant is the constant times the variable. The variable in this case is x. Then over here, I don't have a rule for this, but if I use u substitution, I do have a rule for this. Because I see a function nested inside another function. I'm taking the cube root of x minus 3. So I might be able to do this if I let u equal x minus 3. I know this is going to work because if I take the derivative of x minus 3, I just get 1. So du happens to be 1 times dx. So this is a u to the 1/3, and dx and du are the same thing. So I can write this in terms of u pretty easily. Now, if you have a definite integral, you need to change your bounds as well. These are x values. This says x goes from 6 to 7. When we change our integral into an integral in terms of u, we need to know where u starts and where u stops. So we will substitute x equals 6 and x equals 7 into our formula for u and use that to find our upper and lower bounds. So when x is 7, we get u equals 4. When x is 6, we get u equals 3. So this is, oops, and this should be evaluated on the interval from 6 to 7 as well. So I'll bring that down. I'll do that in a little bit. So we have a new lower bound of 3 and a new upper bound of 4. This is a u to the 1/3 power. And dx and du are the same thing, so we just replace the dx with the du. And that's a special case. It's not always the same. It just happens to be the same for this choice of u. So now we'll just use the power rule here. So you want to add 1 to the exponent. 1 plus 1/3 is 1, or 1/3 plus 3/3, which is 4/3. And then you want to divide by the new exponent. Dividing by 4/3 is the same as multiplying by 3/4. You want to evaluate from u equals 3 to u equals 4. So over here, if we substitute in 7, we'll have 7 squared over 2, which is 49 over 2, minus 7 times 7, which is 49. Minus 6 squared over 2, 36 divided by 2 is 18, minus 7 times 6, which is 42. And then here we're subtracting what we get from the fundamental theorem of calculus here. So we have, if you want, you can factor out the 3/4 as well. 4 to the 4/3 minus 3 to the 4/3. Okay, so that's our answer. It's just not simplified. And then we're going to do the same thing over here. Now we've already computed the antiderivatives of both of these pieces. It was just in a different order. So we can do this pretty easily. Again, if I just use a u substitution for this piece, where u equals x minus 7, du is equal to dx. When I substitute in 8 for x and 7 for x, I don't know why I put a 3 in here. I keep putting a 3 in there. I'm sorry, guys. It should be a 7. That should be a 7. And that would make this 7 minus 7, which is 0, and 6 minus 7, which is negative 1. I'm so sorry. I caught my mistake when I did it over here. So that would make the upper limit a 0 and this lower limit a negative 1. 0 and negative 1. I'm sorry about that. And this is going to be a 0 to the 3/4 power, and this is a negative 1. 0 to the 4/3 power, and a negative 1 to the 4/3 power. Okay, and we'll simplify that in a little bit. I'm sorry, this is so messy this time. All right, so now I'm over here. I'm glad I caught that mistake. Substitute in 8 for x, substitute in 7 for x, and we get a 1 here and a 0 here. So we end up with the integral from 0 to 1 of u to the 1/3 with respect to u. Add 1 to the exponent. Divide by the new exponent. Dividing by 4/3 is multiplying by 3/4. Substitute in u equals 0 and u equals 1 and subtract, and you just end up with 3/4. 3/4 minus 0, which is of course 3/4. Okay, so there's that. And then for this piece, we want to add 1 to the exponent and divide by the new exponent. The antiderivative of 7 is just 7 times our variable. And then we're going to evaluate all of this from 7 to 8. So at x equals 8, we get 64 divided by 2, which is 32. And we've got a negative sign, so it's going to be a negative 32, plus 8 times 7, which is 56. And then we're going to subtract this evaluated at x equals 7, 49 over 2. It's negative 49 over 2, plus 7 times 7, which is 49. So we end up with 56 minus 32, which is 24. And then we're subtracting 49 minus half of 49, which is half of 49. Okay, so we've got this here. And of course, 0 to the 4/3 power is just 0. If I take a negative 1 and I raise it to the 4th, it's going to be positive 1. The cube root of positive 1 is 1. So this is going to be minus 1. We're subtracting 1 there. All right. And so we've got 49 over 2, or half of 49 minus 49. We're going to end up with negative 1/2 times 49 there. And then we have where we're subtracting 18 from 42, or we're subtracting 42 from 18, excuse me. So we would do 42 minus 18. So that's going to give us a 24. And since this is larger, it's going to be a negative 24. So we're subtracting a negative 24. That means we're adding 24. And then here we have a negative 3/4 times a negative 1. So it's going to be a positive 3/4 plus another positive 3/4 plus the 24 minus the 49 over 2 from before. All right, so we actually have the same thing twice. We have this here and that there. So we could just multiply all of that by 2. So this is going to be negative 20 or negative 49 plus 48 plus 3 over 4 times 2 is going to be 3 over 2. So this is, of course, negative 1 plus 3 over 2, which is going to give us a 1/2. Okay, so the answer is 1/2, and I'm sorry about the error that I made here, but I hope you understand the idea. The first thing you need to do is graph the two functions, and then you want to be very careful. Don't just substitute the f and the g into your formula, because in that formula, f is the top function and g is the bottom function. So when you're finding those areas, you need to think about which one's the top function and which one's the bottom function. And since that switches, since the top function is the line here and the top function is the cube root function here, we have to do two integrals. On the interval from 6 to 7, we use the equation of the line minus the equation of the cubic function or cube root function. And then over here, we do it in the opposite order. But once we set that up, this just requires some basic rules, and this requires a u substitution. And then we're doing the same u substitution over here. But notice that since we're dealing with definite integrals, while the antiderivative is still 3/4 times u to the 4/3, the bounds change, so we get different results. Another way that you could do this is you could say that by symmetry, this is going to be the same as this, and you could just evaluate one of those integrals and double it, which is the same thing that we saw here. This was the result of the first integral, and that was the result of the second integral. We saw the same result twice, so it's like taking one of those and then doubling it. But then, yeah, after you do the u substitution, you use the fundamental theorem calculus, you use the fundamental theorem calculus for this piece and this piece as well.